Okay, thanks Wiley for the kind introduction. Today I'm going to present the millisecond radio sky, faster radio burst, and beyond. And in the beginning, I'm going to review the important discovery of the FRBs in the past decade. And after that, I'm going to highlight a few repeaters with very diverse properties and how the VLBI can make the impact. After that, I'm going to mention the ongoing ASIAA FRB project, including the Auriga station in Hawaii that will make the effort for the FRB VLBI, and also the BRST project, the Broadbeam Radio Survey Telescope. And finally, I will sum up the conclusion. So the first FRB was discovered in 2007 by postdoc astronomer looking at the archival data in the PASS telescope in Australia. And this is the FRB signal that the signal is around 1.4 gigahertz, and the high frequency signal arrived earlier than the lower frequency. And this is due to the dispersion. And the time delay between the two frequencies can be described by the formula here, that a quantity times the frequency inverse square difference, and with the parameter so-called dm. So the dm here is the dispersion measure, which means the electron current density integration along the line of sight from observer to the source. And in the archival data, what they do is they will try the different trials of the dm. With the correct dm, then all of the signal across the different frequency will align well in the same time. And by integration of over the frequency, then we will seek the peak in the time series. So what they find is the dm of this FRB is 15 times larger than the galactic contribution. And also the telescope was pointing to high galactic latitude. Therefore, this source is from extragalactic origin. And in the time series, the width of the burst is about 5 milliseconds, and also the flux is about 30 Jansky. So from 2007 until 2017, in the 10 years, only about 30 FRB were discovered. And the majority were reported by the PASS telescope because they have lots of exposure time. And only just a few reported by a few other telescopes like the Arecibo, ESCAP, Green Band, and Atmos. And as you can see, the early distribution of the FRB in terms of the galactic latitude and longitude is like the randomly distributed. However, we don't know where are they, and therefore we cannot understand what's their local environment and what's the local properties. One thing I want to highlight here is for the Green Bank telescope. So I discovered this FRB, and this FRB is the first FRB paper on Nature. Until now, there are already 18 FRB papers on Nature just in a few years. So this field is right now expanding, and there are a lot of opportunities. Our title here is the dense magnetized plasma associated with a faster radio burst. We look at the Green Bank telescope 21 centimeter data set, and this data set is from 700 to 900 megahertz. Before this discovery, all of the FRB were detected at 1.4 gigahertz. So our detection is like in a new band. And what we did for the search is that we apply the 3D dispersion algorithm, that we convert the signal from the frequency time domain into the dispersion measure versus the time domain. So for the real signal, for the real astrophysical signal in the DMT domain, it will concentrate the power at a specific dm. However, for the radio frequency interference, you can see the signal will extend it in the DMT domain. So it will be really easy to distinguish between the noise and also the true signal.
Sorry.
Yes?
Could you go back to one slide. I just wonder, were those FRB, the previous, like these 30 FRB, were they detected by chance, or actually those some observations are designed to detect those?
So actually, it's just like the blind survey, and also in the early stage, post-astronomer, they just look at their archival data. Yeah. Okay. And there are three important impacts from our discovery. The first two is the first detection for the rotation measure and also the polarization precision angle swing. So what is rotation measure? It means that when an EM wave propagates through a B field, then the EM wave phase will rotating by an angle beta. And this beta angle could be described by the parameter rotation measure times the wavelength lambda square. And in the Stokes parameter in our data, what we see is the Q and U, they show the lambda square pattern. And for the rotation measure, the quantity we got from this FRB is 10 times much more than the galactic contribution. And therefore, this source is extragalactic origin, as well as has the dense magnetized plasma associated with it. Another interesting thing is the polarization precision angle, that in the data set, not only we fit the rotation measure, but there is additional parameter that describe the polarization precision angle that in terms of time. So what we notice is that this is the post profile in terms of the time series. And you can see the polarization precision angle, the PPA, is changing over time. And this can be explained by the magnetic vector model, that when the source it is rotating, then the B field is also rotated. And this has been seen in pulsars. So after our discovery, there are two more Nature papers to confirm that the high intrinsic rotation measure and also the PPA swing. The first one report is the extremely high RM for the first repeater 121102, and the rotation measure is up to 10 to 5 radian per meter square. Interesting thing is they don't see any PPA swing in their polarization data, and this was reported in 2018. In 2020, the FAST group using the FAST telescope in China and do a follow-up study on a repeater, and they find that the polarization angle swings is very diverse for this repeater. So for example, for this one, the polarization angle is increasing, but this one is slightly decreasing, and the property is quite diverse here. And the third impact from this detection is the two screens model, that before this discovery, people already see the scattering in the FRB, but we don't know whether the scattering material is uniformly distributed along the line of sight, or it is concentrated inside of the host galaxy. So what we notice is that this FRB shows the scintillation pattern. So the local view are around 750 megahertz, show the scintillation pattern across time. So scintillation means the intensity is frequency dependence. And when there is the scintillation, it means the second screen, the first screen is unresolved by the second screen, because the first screen, the angular size is very tiny. And for the scintillation property here, we measure the decorrelation bandwidth is about 1.2 megahertz, which is consistent with the galactic pulsar that is only 2 degrees away from this FRB. And to convert the decorrelation bandwidth into the scintillation timescale, we can get by 1 over the decorrelation bandwidth, and therefore the scintillation scale is about 1 microsecond. However, in the scattering timescale, we measure the scattering time is about 1.6 millisecond. So scintillation timescale is microsecond, but scattering timescale is millisecond. So it is very different. And therefore, we said that the scintillation happened at the Milky Way, but the scattering is inside of the host galaxy. There should be a dense material inside of the host galaxy instead of uniformly distributed along the line of the star. And we propose that it could be like a compact nebula. And so far, we are looking for additional nature paper to confirm this this discovery.
Why is dispersion that can figure it occurs within our galaxy, and the other one is coming from the host galaxy?
So the dispersion is including every electron along the line of sight, from observer to our galaxy, and then the IGN and to host galaxy. So that is the hosting. But the key thing is the scintillation. So the scintillation, the pattern here you can see the overall signal is frequency dependence. Yeah, and this frequency dependence we can get the decorrelation bandwidth, and this decorrelation bandwidth is consistent with the Milky Way pulsar. And the scintillation happen is because the angular size. Yeah. Yes. Okay. Yeah. Okay. So that is the story from 2007 to 2017. That the GBT FRB make the impact, and we still wait our other FRB to confirm more information from our first discovery. And from the 2018, the game changer comes, the CHARM FRB. In the past 3 years, the collaboration already published 4 Nature papers. And the CHARM FRB the full name is the Canadian Hydrogen Intensity Mapping Experiment. The telescope is located in the British Columbia in Western Canada. The telescope is composed by 4 cylinders. Each cylinder is about 20 meters times 100 meters, and therefore the total collecting area is around 8,000 meters square, with system temperature about 50 Kelvin. So each cylinder has 256 beams. And for each beam, we have 2 linear polarization with 1024 frequencies that across from 400 to 800 megahertz. And this is the signal path for the CHARM telescope. The telescope is looking at the sky, and we got the radio wave come to the cylinder, and with the polarization information. Then after the digitalization and also the FPGA, the GPU correlator will correlate the signal and output the data for 3 different groups, including for the cosmology, the 21 centimeter purpose, and also the FRB collaboration, and also for the pulsar team. So for the FRB collaboration, we have 1024 intensity beams that are coming from the 1024 receivers, and we have 1 millisecond time sampling. So the key thing for the CHARM's successful story is because of the large field of view. Right now, the CHARM telescope can detect a few FRB per day, but just a reminder, from 2007 to 2017, in 10 years, there were only 30 FRB. In other words, only a few FRB per year. But right now, it's a few FRBs per day. So for the CHARM telescope, the field of view from eastern to western is about 1 to 2 degrees. It's frequency dependence. And from the northern to the south is about 110 degrees. So the overall field of view is much higher than the traditional, like the single beam telescope. And because the CHARM telescope is on the ground, so when the Earth rotates, then the field of view is also rotates. And the key thing is the source transit duration depends on the declination. So if the source is located at the equator, then every day CHARM will have 5 to 10 minutes exposure time with the main beam. But if the source is in the North Pole, then the CHARM telescope will monitor it 24 hours.
resolution? Angular.
Angular resolution, it depends on the location, and also because we have 4 cylinder, so the angular resolution typically is arc mini. Typical, yeah, but it's complicated, yeah. Mm-hmm. And recently we published the first FRB catalog that from 2018 July to 2019 July, we have 474 apparent non-repeaters. And also, we also report 62 bursts from 18 repeaters. And the inferred event rate is about 1,000 FRB per day per sky. This plot just shows you the distribution in terms of the declination and the RA. The circle here is for the non-repeater, and the triangle here is for the repeater. And as you can see, the sample here is like quite randomly distributed. So from the catalog, we report there are 4 types of morphology. So this is so-called the waterfall or dynamic spectrum, frequency versus time after the dispersion. The type 1 is just very simple broadband, that the signal is like across the whole band. And also there is only like the single peak in the time series. And this has been only seen in the non-repeater. And the second type is the simple narrow band, that the signal is only in a partial band, and with a very simple timing structure. For this one, we already seen in both non-repeater and the repeater. The third type is temporally complex, that there could be multiple components or complex structures in the time series. And the last one is so-called downward drifting, that initially the signal is narrowband, but across in time it's shifting down. And this downward drifting has been observed in many repeaters. So this is a gallery for the non-repeater versus the repeater in our catalog. For the non-repeater, we can see some of them show the scattering tails, but others show there is nothing for the scattering tails. And for the repeaters, we notice a lot of them are only like the narrow band. And also, many of them shows like the drifting pattern. So for the drifting pattern, it's still a mystery. Some people think could be like the intrinsic mechanism, but others argue it could be like from the propagation effect. So it's still an opening question in our FRB field.
Wait a minute. I thought drifting would be a normal phenomenon because you go through the plasma within our host galaxy.
I think you will refer to. I think you are referred to like the dispersion curve, but yeah, but
When you say drifting, maybe
yeah.
different.
But for this drifting, this is after we de-disperse with our initial DM. Yeah. So, yes.
For the repeaters, do they show the same characteristic every time?
No, it's changing a lot. So, for example, I think these 10 are from the same repeater. Okay, but you can see the emission center is also drifting, and also some of them just show a very weak signal without drifting, but this one shows a very strong drifting. Yeah, so it varies a lot, and we don't know what happened there. Yeah. So the histogram here summarizes the comparison for the non-repeaters and the repeater. The 2 upper left panel here is the histogram for the RA and the DEC. So both of them are, for both of the non-repeater and repeater, they are underlying the same statistical distribution. These 2 is for the total DM and for the extragalactic DM. And they are also underlying the same statistical distribution. The panel here is the bandwidth versus the counting in log scale. So this one, we can see the statistical property is inconsistent. And this one is for the scattering time, histogram, and also for the fluence. So for the scattering time and the fluence, they are underlying the same statistical distribution. And the last one is the flux. So for the flux, it also shows the repeater and the non-repeater. They are a bit inconsistent with the statistical distribution. Probably it's due to the repeater pulse width is a bit wider. So this plot summarized that the repeater usually shows a larger width and also a narrower bandwidth in the spectral profile. So what we do is that we analyze the spectral profile by using the parallel with a spectral rounding index. And we compare the spectral rounding index and the intrinsic width distribution for both of the repeater and non-repeater. So the green dot here is for the non-repeater, and the origin dot here is for the repeater burst. The purple one is for the repeater with their first detect burst. So as we can see, the repeater usually has a wider width, and also their bandwidths are narrower. So what are FRBs? There are a lot of models, and the theory community is very actively trying to understand what's going on with FRB. Popular model including like the magnetar and also pulsars in our galaxy, and also like the supernova or emergent black hole for the non-repeater scenario, but still there could be some unknown. And this website is a very active website. Any theorists are welcome to contribute your own theory on this website. And also, this website summarizes the prediction from different theory that for observer to looking at. So in the following, I'm going to mention a few very interesting repeaters. And the first one, obviously, I'm going to talk is the first repeater, the 121102. So this repeater was initially reported by Arecibo in 2014, and they do a lot of follow-up and find it is repeat in 2016. And as you can see, the dynamic spectrum is changing. So even it is from the same repeater, the property is still changing a lot. And later in 2017, the VOA localized this repeater into a dwarf galaxy with redshift of 0.2. And the EVN show that there is a persistent radio source associated with this repeater. And another interesting follow-up is for the rotation measure. So initially, the rotation measure in 2017 was about 10 to 5 radian per meter square. But across 3 years, it decreased by about 30%. So in 2019, the rotation measure is about 0.7 times 10 to 5. And one thing very interesting is around 2018, that the rotation measure was observed that increasing a bit, but decreasing again. Meanwhile, in general, the RM is decreasing, but the DM has been observed to be increased a bit from 461, and right now it's around 463. And 2 weeks ago, there is another Nature paper on this source. So this was reported by the FAST telescope in China, that they spent about 60 hours, spanning 50 days, and they catch about 1,700 bursts. So the panel A here summarizes their observation, exposure time, and the gray bar here means there is no observation. And the panel B here is the inferred burst rate. So they find that the burst rate is highly clustering. So sometimes the burst rate could be up to 100 bursts per hour, but other times could be only 1 or 2 bursts per hour. And we don't know what's the mechanism for these very different clustering event rate. And they analyze the burst energy across in time. And the penalty here is the density of the energy distribution. And they find there are like the two peaks in the burst energy distribution. And because they have a lot of bursts, so what they can do is to search for periodicity. They try to search the periodicity from 1 millisecond to 1,000 seconds, but they do not detect any convincing result.
Do they have a special resolution? I mean, the pointing direction.
Pointing direction?
I mean, you have 1,700 birds.
Yes.
And so these birds are coming from different directions in the sky.
No, this is from the same source, the same repeater.
Oh,
Yeah,
same repeater.
the same repeater, the R1.
Oh, okay.
Yeah.
I see.
And the sudden activity is not only be seen in the R1, but also from another repeater. So recently, CHUM FRB detect a sudden activity in this repeater, which is initially detected by CHUM in last November. And the upper panel here just show you the exposure time across in date. So the date here is from 2018 September up to 2021 May. And the gray bar here just marks the detection in the CHUM. So the initial detection is around 2020 November, but you can see there are a lot of detection around late March. And right after we find the sudden activity, we report to the community on the ATEL, and a lot of telescopes do their follow-up simultaneously. So ESCAP quickly localized this repeater just in a few days. And the follow-up by the VOA and also the GMRT find there could be a potential coincidence with the persistent radio source. However, the EVN do the follow-up and say there is no PRS association. So the lower panel here summarize the follow-up observation by different telescopes in a few days. So the timescale here is April 2nd up to April 7th. And you can see the detect frequency is also quite different. So two things I want to highlight here. The first thing is our GMRT collaboration, we spend 4 hours and we detect 48 bursts from the same repeater. And also you can see the dynamic spectrum is quite diverse. It shows like the different properties. And the second thing is the PAX telescope with the ultra-wideband receiver. So the ultra-wideband receiver is down to 700 and up to about 4 gigahertz. The very interesting thing comes from the ultra-wideband receiver by the PAX. So the upper panel here is the FRB signal that detect in 1 hour. And the lower panel here, the black line for each of the poles is the intensity. And the red line is for the linear polarization. The blue line here is for the circular polarization. What they find is that the circular polarization suddenly show up in the last burst. And the circular polarization is about 45%. It's very high. And this is the first time that the circular polarization is observed from a repeater. The next repeater I want to highlight is the galactic magnetar SGR 1935. So in 2020 April, in the afternoon, we suddenly saw an extremely bright event come to the CHUM. 93 over 1024 beams were detect the signal. And quickly we localized the source into the magnetar. And the interesting thing is the CHUM is here in the Western Canada. But when we do the localization, we find this event is from the silo event, that it is not on the meridian. And the source was on the meridian of Pacific. So this plot shows you the dynamic spectrum of the detection of the brightest beam of the CHUM FRB. frequency versus time. You may notice the pattern here is quite spiky. This is due to because we observe in the side lobe. So the spectrum here is the product of the beam response and also the intrinsic property. And because in the Ontario, we have a 10-meter dish that for the purpose for the FRB BLBI, I will describe in later. So we have the 10-meter dish that's pointing to the Trump meridian. So simultaneously, we detect the signal. And because in the ARO, we record the voltage data. So we have the baseband, we have the polarization information. And the rotation measure of this source is about 1/16. And right after report to the community on ATEL, then the Caltech group, the report, they also detect the burst in their STAR-2 experiment. So STAR-2 are 3 dipole array looking at the sky, deployed in the California and Utah. So this is the signal let's see. So our band is from 400 to 800, and for the STAR-2, their band is around 1.4 gigahertz. And due to the very steep spectral index, what they detect is only, let's see, the second component. And meanwhile, the higher frequency, like the hard X-ray and also the soft gamma ray, they also detect the 2-component burst. But for the 2-component burst, is about 3 milliseconds earlier than the radio detection. And the SGR discovery fulfill the gap between the magnetar and the FRB. So what we see here is the observed frequency versus the distance. And typically, the FRB have the energy around 10 to 35 to 10 to 41 erg/second. And for the SGR, the energy scale is also quite close to 10 or 35 erg/second. Another thing, the impact is from the BLBI, is that recently the EVN localized a very nearby repeater into the globular cluster of M81. So previously, people are thinking the FRB could be from magnetar, but for the globular cluster, it's like an old population, but magnetar is like the young population. So they argue that this FRB could be like from the supergiant pulses from millisecond pulsars. So for this repeater, initially it is reported by the Trump, and the Trump localization is only in the Archimedes resolution. And inside of the region, there are 4 possible candidates, including the M81H2 region, X-ray source, and the globular cluster, and also the point ratio source. And the EVN just find that the burst is localized into the M81 globular cluster. So later, the DSN follow-up confirmed the connection to the pulsar scenario. So the burst here just show you the frequency and time, but the time resolution is very high. So right now, this is from minus 50 microsecond up to 50 microsecond. And if we look at the high time resolution with 0.1 microsecond, then we will see there are 7 components inside of this burst. And the multi-component is very similar to what we already see from the Crab pulsar nanoshoot. So nanoshoot means the giant pulse emission with the nanosecond time scale. And the plot here just show you an example for the nanoshoot reported by the Arecibo. That you can see the scale here is a few microseconds across 2 gigahertz. But we can see there are multiple peaks across this time duration. And in some cases, the flux of the nanoshoot could be up to 10 to 5 Jansky. So for this repeater, it is the closest repeater up to date. And also, it fulfills the gap between the FRB and the Crab nanoshoot. So the line here just shows you the brightness temperature from 10 to 45 down to 10 to 35. So typically the FRB, they have the brightness temperature around 10 to 37. And the recent detection from this burst show that the brightness temperature is quite close to the Krebs nanoshot. So another interesting repeater is for the band changing behavior. So this FRB was reported by the ESCAP initially, and it shows the bandwidth is about 150 megahertz. But later, after 3 weeks, they do the follow-up and find that the bandwidth of the repeater decreasing into about 70 megahertz. So to connect the band changing behavior between FRB and the pulsar, recently my student and I, we published a narrow band joint pulses from the Krebs pulsar. So what we do is we're looking at the ARO 46-meter data set from the Krebs pulsar, and he do the search and found about 1,600 joint pulses, like a broadband, but 6 of them are narrow band. And how can we connect the band changing repeater to our case? That we provide the dimensionless parameter, the delta nu over nu. So the delta nu means the full width half maxima of the spectral profile, and the mu means the spectral center of the spectral profile. We found that the 6 narrowband Krebs pulsar has the delta mu over mu from 0.1 to 0.2, and the band changing repeater here, the delta mu over nu is about 0.05. So the final repeater I want to mention is the periodicity behavior that our collaboration published a Nature paper to describe the 16 days repeating periodicity. So the gray bar here shows the predict epoch from 2018 October up to 2020 February, and the triangle here marks the detection, and they are aligned very well. So the possible scenario including like the binary system or from the precession of the neutron star. And this year, Europe team, they do the follow-up and find a very interesting the chromatic periodic activity. They do the observation at the 1.4 gigahertz and also 150 megahertz. They find that the higher frequency signal arrive in the earlier periodic phase, and the lower frequency signal come to later periodic phase. This plot just shows you the activity window versus the phase in terms of the frequency. So high frequency, the green one, is earlier than the red one, the lower frequency. So in this July, our China FRB collaboration submit another Nature paper that we find sub-second periodicity. And up to the submission, we haven't seen any repeating event from the source. So what we see is the pulse here is about 2 seconds, but we can see there is like a duplicated peak here. And the period is about 200 milliseconds for this one. But for this one, the period is around 3 milliseconds. And the last one, the period is about 10 seconds. And our result will favor the emission of FRB could be from the neutron star magnetosphere. And also, it could be like from the supergiant pulses from millisecond pulsar and interacting in a binary system. So to really understand the nature of FRB, we want to do is to understand their local environment. And the key thing is the BLBI. So right now, our team is working on the Chang FRB BLBI that we will have we have the main station in Chang, and also the ARO 10-meter dish in the Algonquin Radio Observatory in Ontario in Canada. And another Auriga station is in the Green Bank Observatory in West Virginia that we deploy at 6-meter dishes and simultaneously looking at the Chang meridian. And just in and for the calibrator, right now we are using the Krebs joint pulses because they are very bright. And in this June, the Chang FRB and also the Auriga station detect a very bright FRB. And currently, we are still working on the localization. And right now, we are trying to understand like the clock stability and also the ionosphere distribution. So the plot here just show you the correlation of the signal, normalized signal, versus the lag. The first panel here is the jump pulse from the Crab pulsar detected by the CHARM and the ARO on May 29. The second panel here is the FRB signal detected by the CHARM ARO on June 3rd. The third panel here is the Crab jump pulses on the same day of the FRB detection. And last panel is the Crab jump pulse correlation 1 day after the FRB detection. So what we can do for ASIAA is that we are going to build up an outrigger station in Hawaii, Big Island. So the Hawaii Big Island is here, and the station is like in the eastern south corner of the Big Island. And the setup will be similar to the GBO setup, that the field of view will have about 5 to 10 degrees. And we expect it can detect a few FRB per month. Current status. Right now, the dish antenna is being fabricated in China, and also we are fabricated on the front-end component. For the real-time data processing system, it's being assembled in Hilo, and for the site, it's being developed. In addition, we have the Broadbeam Radio Survey Telescope 200, that we will have the 200 dipole array and have been under development looking at the whole sky. So the key thing here is the whole sky. And we expect it can detect a few FRB per day, like the similar event rate of the CHARM FRB. The panel here just summarizes the current status with other telescopes. Field of view versus the SEFD and also the effective area. Dashed line marks the event rate from 100 FRBs per day, 1 FRB per day, to 0.01 FRB per day. Solely, the triangle are existing survey. So for the existing survey, the best one is the CHARM, which can detect a few FRB per day. The rectangular ones are the ongoing project, and they're like the DSA and the HIREX project. And there are also some proposing dreaming project, not funded yet here. And for the BRST project, initially we are going to work on 200 dipole array. This can give us the same event rate as CHARM. But ultimately, we are looking for 2,000 elements that we can get about 100 FRB per day. So for the 200 element, the current status that we are developed the dipole antenna in ASIAA, and also the front-end components is to be developed. And for the real-time data processing, it's being developed in different places. And for the site, we are also going to develop it.
So these are just single telescope components?
You mean like,
That
yeah, in terms of single telescope, yeah. So what's the scientific impact from BRST? Firstly, because it has the all sky monitor, so it can tell us do all FRB repeat? Are there different types of FRB? And with the outrigger station, we can do the localization not only for the host galaxy, but also pointing to the local environment. So this can also tell us like the cosmological distribution and also the local information. For the FRB application, it will be interesting to look at the lens FRB. So for the lens FRB, it means from FRB to the observer, there is a lens system. The first scenario is the macro lens, that like the supermassive globular cluster, galaxy cluster, or like a heavy galaxy. So currently, astronomers are using the quasar and to understand the lens system as well as the cosmology. But for us, but for the quasar, the precision is only in terms of hours. However, for the FRB, because it is coherent emission source, and we have the baseband data, so the timing precision can up to nanosecond. So we will improve the measurement from hours precision down to nanosecond precision, and it can better measure and constrain like the H0 and also the dark energy. The second scenario lens is for the micro lens FRB, which means there is an extragalactic planet or extragalactic stars along the line of the side. And for the mass range from 1 to 100 solar mass, the time delay of the image could be from microsecond to millisecond, and we will see like the multiple components in the data. And if the lens FRB they are repeater, then we can continue monitor the sensors, and we can see the time evolution of the lens system. So right now, it's the right time to do the right thing in the right place. If you want to join us, we have the upcoming ASIAA FRB online data camp. So for this data camp, we will learn how to find the joint pulses from the voltage data, and there will be two sections. The first one is to teach people how to read the specific VD file, and how can we do the coherent dispersion that convert the signal from dispersed signal into the joint pulse here. And this data is from the real data from the ARO 10-meter dish, will be essential for the FRB BLBI, and also the technique could be very useful to find more FRB in the future. For the section 2, we will use the HPC cluster to search for joint pulses with several minutes data set. And we encourage and welcome people with experience in Linux and also Python to join us. The tentative time will be around middle November, and it will be determined by all of the participants. And especially thanks to the HPC committee of the theory group and the SAM for their kind support. If you are interested in joining this online data camp, please contact with me by this Friday. So I'm going to sum up my talk here. In the past 10 years, about 600 FRB of repeater and non-repeater have been published. They show very diverse properties, and no any single theory can explain all of the property we observe. Do all FRB repeat if we observe as long as possible? And also, are there different types of FRB? They are still like the opening question in the community. And the large field view will give the benefits of large sample, like the Trump FRB successful stories. And the VLBI will be the key to really understand FRB. Currently, the EVN only look at the repeater, but ASIAA will contribute to understand the non-repeater by building up an Auriga station in Hawaii. And in addition, we also have the BRST 200 project in ASIAA that will look at the whole sky simultaneously, and it will open up the new window on FRB. And we welcome everyone to join us with this project, and also we have the upcoming data camp. So thank you for listening, and I'm happy to take questions.
So you mentioned one repeater with decreasing rotation measure with increasing
DM.
dispersion measure. So this means that the magnetic field decreases, right? Or not necessarily?
Not necessary, because the rotation measure is like a vector, and therefore it can be like a different component combination along the side. Some component can increasing, yeah.
Okay, so it could be if the direction of magnetic field like changing
Yes.
or something.
Yeah, yeah.
But I suppose people can use this property to infer the original at that system. I mean, so sorry, let me ask, so this is the only repeater having that property?
This is the only repeater shows so dramatic change, but publish,
Okay.
yeah, publish.
Okay. And I suppose people build theory to try to explain that behavior.
Yes, yes, but some theory only predict the simultaneously decreasing or increasing for both of the DM and RM. but there is no good theory for increasing DM, decreasing RM yet.
Okay.
Yeah.
Thanks.
Yeah.
So you show that the FRBs have very diverse characteristics, and there could be multiple scenarios explaining the origins. So I wonder, among those, which one is the most exciting one, or which one really brings in the new physics?
So I think the answer is time dependent. So in 2020, people thought magnetar would be the popular model for FRB because magnetar typically will show dramatic properties. Sometimes it can emit very high energy bursts in X-ray and gamma ray. But this one is the first thing in the radio band. However, in this year, the EVN localized a repeater into the globular cluster. And this one will suggest not only magnetar can produce FRB, but like the millisecond pulsar can also produce FRB. However, we haven't seen any FRB from known millisecond pulsar in our galaxy. Yeah, so it's still a mystery. Yeah.
Is there any optical counterpart or very different frequency?
Yes. Yeah. So the counterpart that I didn't mention here is like the right after the VOA and the VLBI localization, optical telescope can do the follow-up and to see the host galaxy. Yeah. Yeah. But
So,
yeah.
I see.
Yeah.
Okay. So only host galaxy, no which galaxy.
Yeah. Yeah.
But no specific other information than localization.
It's very limited. Yeah. And also so far it's known for repeater. Yeah.
Of course.
Yeah.
Yeah, so since you can localize the host galaxy, yes, the number is not big, but could you already study the property of local galaxy and get some idea or get some constraint what kind of sources would be? So there are massive galaxy or dwarf galaxies, so on.
Yeah. So, but the problem here is only 20 repeater or only 20 FRB have been localized over 600 known FRB. So the population of the host galaxy is still quite limited. It's only like 3%. And
So
yeah.
like 20 is
Yes. Yes.
a
Yes.
sample, right?
Yeah. So. So for the SCAP group, because they can localize the FRB into their host galaxy, and they have just a few FRB with the host galaxy information. So what they propose is that FRB can like tracking the missing baryon, like from the IgM problem, because we will know like the galactic contribution, the DM, and then we can infer how many is the remaining along the IgM. So what they do is they plot the DM of the cosmic contribution versus the redshift, and they see like a relation here. Yeah, but the sample here is quite limited, and also right now the highest redshift is only about 0.66. Yeah.
Sure. I think the question was, is there any, are all these galaxies ellipticals, or are they all spirals, is there anything magic? And I think the answer you already said earlier is that for some of them we know them to be in a globular cluster, so we know a lot about what's going on. And some of them, the first one you described, R1 is in a dwarf galaxy. So the extremes, everything is, among those 20, everything happens. So no information, no useful information.
Is it correct to assume that once you correct for the dispersion measure, all the variability you see are intrinsic to the source?
It will be really hard to say because even for the intrinsic, we are not sure whether there can be multiple distribution. Yeah.
I was going to suggest that if they are intrinsic and there's something physical, this sample sounds like a great project for machine learning type of classification stuff.
What did you mean by that?
No, so the variability of signals, the
Yes.
patterns, there's just so many, right? If
Yes.
you want to classify them
Yes.
in a meaningful way, machine learning seems like a useful tool.
Yeah, machine learning could be very helpful